Back in 2023, I was in my loft and I came across my original Amiga 1200 from the early 90s. To my surprise, it still worked, and this really set in place a series of events which led to me porting OutRun to the Amiga hardware. Now, I'd already worked on the OutRun codebase before. I had worked on the enhanced edition for the arcade machine. I'd worked on Cannonball. So I did have a good starting ground, but I didn't really know the Amiga hardware well. So this was a learning exercise, and I didn't know if I was ever going to finish the project. I thought I might hit a technical roadblock or get bored or something. But as it turns out, I did finish, and I think now is the time to talk about some of the techniques I used along the way and how it was done. I'm also providing some source code so you can code along at home. So without further ado, let's get into it. OutRun's arcade hardware was an absolute beast. It was first released in 1986, the year after the Amiga first launched, and it represented an evolution of Sega's so-called superscalar technology, which had previously powered Hang-On and Space Harrier. Its signature feature was the ability to scale hundreds of individual graphics or sprites in real time. To give you an idea of how far ahead of home consoles this hardware was, it took until 1996, 10 years later, when Sega launched the Saturn, for an arcade-perfect home port to appear. Along the way, there were many attempts at home ports that fell way short of the mark. If you're lucky enough to be younger than myself and weren't around in the 80s, it's kind of hard to describe just how revolutionary some of the new arcade titles felt. Bear in mind, just a few years before, we still had black and white games in the arcade that, whilst great fun, were incredibly basic in comparison. There was simply no way to experience a game such as OutRun anywhere other than the arcade. The idea of an arcade-perfect port on a home system was pretty much a pipe dream. So let's take a look at the OutRun hardware and see what we have. There is a master 68000 Motorola CPU clocked at 10 MHz. This is responsible for almost all of the game logic and constructing the environments you drive through. However, there's also a secondary 68000 CPU which runs in parallel to the first. It's also clocked at 10 MHz. This CPU is responsible for generating and manipulating the game's road, curves, hills, changing the width and so forth. The two CPUs have their own RAM but also have a shared RAM area so that they can communicate between each other. And today we're going to be focusing on how the road for OutRun is created. The fact that Sega dedicated an entire expensive CPU just to the task of drawing the road shows how important and powerful this piece of the hardware was. However, it's not really the CPU power which was responsible for making OutRun the tour de force it is. It's also the custom graphics hardware that the pair of CPUs command. The graphics hardware does most of the heavy lifting when it comes to manipulating graphical data at insane speeds. The main areas of the graphics hardware include the road generation, sprite rendering and scaling, two independently scrolling tilemap layers, and a text overlay layer. One important consideration when moving huge amounts of data around, which is necessary for a game like this, is memory speed. Now, to provide a comparison, a stock Amiga's graphics hardware uses chip RAM. This provides a memory transfer speed in the range of about 3.5 to 7 megabytes a second. However, the OutRun hardware provides RAM access to the tune of 40 megabytes a second. So it's well over 10x faster than a stock Amiga. It's easy to focus on CPU power, but fast access to data is equally important, if not more so. From an architectural standpoint, this hardware is insanely more powerful, and the Amiga was indeed a powerful home computer when it launched. But OutRun's sprite frame buffer can be filled to the tune of 90 megabytes a second, and this is still faster than most of the Amiga accelerator cards that are being produced even today. I hope this starts to provide a picture of why porting OutRun to the Amiga architecture was such a challenge. The graphics hardware was light years ahead of what Commodore delivered. This meant that I would have to try to recreate the graphics hardware functionality in software. Not only that, but a single CPU would have to handle the functionality of the two 68,000 CPUs, a Z80 CPU, and a plethora of custom graphics chips. So, onto the final CPU of the original hardware. It's a Z80, similar to what would have been in a Spectrum home computer or an arcade game like Pac-Man. But in this case, it is used simply to pass the music data and drive the in-game samples. But we're here today to talk about the road generation. Now, there is actually not one, but two road generators on the OutRun hardware. This means that two roads can be drawn simultaneously. Not only that, but there is logic to merge and blend the roads together, so those two roads can become one really wide road. The graphic for each road is contained in an EEPROM on the top PCB. If you wanted to, each road could look totally different. But for OutRun, both EEPROMs contain identical data, and so each road looks identical. So let's take a look at what the contents of each of the identical road EEPROMs look like. As you can see, they contain a basic graphic of a road disappearing into the horizon. And that's it. That's the only graphical visualization stored of the road. Everything else you see in the game, the curves, the undulation of the road, the variations in width, are all created in software. However, it's the road graphics hardware that turns that information into the visualization we see on the screen. Let's take an example of a simple road curve. The curve effect is created by dividing our road graphic into horizontal lines. By offsetting each line by a different amount, the curve is created. Effectively, every frame, our game code, run by the secondary 68K CPU, calculates the horizontal offset of every single line of the road to be rendered. Using this technique, we can effectively generate any type of curvature we can dream of from one simple graphic. But of course, we can't stop there, or we'd have an entirely flat road, which would be incredibly boring. So, how do we turn this basic graphic into a road with undulation? Well, think of it like this. In the previous example, we assumed that we were only manipulating the road graphic horizontally. But what if each horizontal line of the final road did not have to map to that same line of the source graphic? Imagine drawing the road on a piece of elastic and then stretching that elastic out from top to bottom. Suddenly, you could create all kinds of interesting distortions and effects. Let's take a look at a simple one. If we're at the crest of a hill looking downwards, it makes sense to stretch out the final visualization so that each horizontal line is drawn twice in the final image. Similarly, in this example, you can see that the brow of a hill is reached. What is happening at this inflection point is that the sampling rate from the original image is suddenly changed, skipping lines from the original source graphic. This causes the road to rapidly disappear into the horizon. Also, we can hide sections of the road to create the effect of a dip. The gateway level has some good examples of this. Moving the position of the horizon is also critical in creating this effect, which is something the road CPU also handles. In OutRun, the horizon can be hidden behind the road, which amplifies the illusion of a change in height. So we've looked at the curvature of the road and creating undulations in the terrain. The final piece of the puzzle is changing the road width. This is a piece of functionality that a lot of simpler racing games bypass entirely. Take Hang On, Yu Suzuki's forerunner to OutRun. The road remains at a fixed width throughout the entire game. Similarly, Lotus 2 on the Amiga. Although the width varies between levels, it remains fixed during each level you play. Remember that we said that OutRun has 2 road generators. Well, these roads can either be drawn independently, creating the effect of 2 simultaneous roads, as you can see at the start of stage 1 and on the Autobahn route. But also, these roads can be seamlessly merged via hardware, mixing each pixel through some custom logic into a massive 3 to 6 lane road. And this here is one of the initial challenges of porting OutRun to the Amiga. We're not just copying road data from the graphics ROM to the screen, the hardware manipulates each pixel along the way. Finally, the effect of moving can be thought of as scrolling a texture downwards over the road. But in reality, it's a line-by-line recolor of the road graphic. This is also performed by the road hardware. Not only does the road hardware colour the road and create this sense of movement in the process, but it also colours the ground on either side of the road and even the sky. Those nice background gradients we see in OutRun, they're also generated by the road hardware. So at a very high level, that's how OutRun generates its pseudo 3D road. It's a 68,000 CPU paired with custom graphics hardware that has been manufactured specifically for this purpose. Now, at a high level, we can simply execute the 68,000 CPU code directly on the Amiga. The piece that's missing is the road rendering itself. On the plus side, the road rendering hardware is relatively simple in contrast with the 68,000 road generation code. However, that simplicity is negated by the need for speed, and the challenge that we've got is producing road rendering code that is insanely fast. And this was far from a simple challenge. I've lost count of how many revisions of the road rendering code I went through on this project, but it was well into the double digits. We're talking major architectural rewrites every time here, not minor optimizations. But I can tell you that I started with the safest implementation just to get things running. And this was actually to port the MAME driver to assembly. It worked as a concept in terms of getting the graphics rendering, but it was so slow. I think it ran at just a couple of frames per second initially. And bear in mind, this was on an 030 processor. There weren't even any sprites in the game yet. There was no game logic. However, as an early proof of concept, it taught me how much work was going to be needed and that I wasn't just going to be able to quickly code up some graphics code and expect OutRun to work well on an 030. Now, if you're being generous, you'll point out that OutRun's road CPU alone is 25% faster than the only CPU in the A500, and that's ignoring the pedestrian memory speed of the A500 architecture, especially when accessing chip memory. But I also understood that from the get-go, this was never going to be performant on that base level hardware. I wanted to make the arcade version of OutRun run on an Amiga. I didn't want to make a conversion that would have been my own interpretation of the game. Just to be clear, I don't think there's anything wrong with that approach. It's just not the project that I wanted to spend my time on. And when you're spending this much time on something, it's got to be the way you want it to be. And I think it's important to call the hardware requirements out, because some people believe it's cheating not to target like a stock machine like the A500. But the reality is, Amigas shipped with trapdoors in the bottom specifically to enable them to be upgraded, and you could purchase processor upgrades for the Amiga back in the day. They aren't a new invention that didn't exist at the time. This hardware spec would have been possible back when the A1200 was a new machine. The main difference now is that everything's got cheaper, so to have an Amiga with 8 megs of RAM costs next to nothing, and it's also much cheaper to buy a 030 processor than it would have been back when I was a teenager. Personally, I don't think there's any cheating involved. To tell you the truth, I think the biggest cheat that any retro developer has these days is access to modern tooling and information. We get to code in modern IDEs like VS Code. We get to make use of modern scripting languages like Python to help us manipulate data, make tools, and automate tasks. And we have access to the internet and a vast community of people, projects, and knowledge. So for me, that's the real cheat I have as a developer. And I hope that as we go into the making of OutRun, you'll understand that if it was that easy to make OutRun run on a single CPU, Sega would have gone down that route in the first place. They were a business, they would have wanted to save the money. So there we go. So without further ado, let's get into it and look at some of the Amiga code. Those of you familiar with the Amiga hardware will know that the Amiga has a coprocessor called the Copper. This is a simple processor with limited functionality, but it is also very cool in that it is synchronized with the CRT video beam. One advantage of the Copper is that as a programmer, you can leave it running its own little program whilst the main CPU goes off and does its own thing. I wrote a very simple list of instructions, known as a cop list, for the Copper to execute continuously. This program would wait until the video beam reached a particular line of the screen and then set the first colour of the colour palette, colour entry 0. This meant that every single line of the display I could display a unique colour. It also circumnavigates the 256 simultaneous colour limitation of the AGA graphics chipset. With 224 horizontal lines, we effectively get an extra 224 colours for free, even though we're repurposing the colour entry 0 on every line. This enables us to recreate part of OutRun's road rendering hardware, namely the ability to solid fill a line. If we fill the entire screen with the colour 0, we can still generate unique background colours and gradients with ease. As part of the first step of reproducing the arcade road hardware, I connected the output of the road CPU code to a newly created 68000 routine. This newly created routine acts as a bridge between the arcade code and the Amiga's Copper processor. Every frame it would poke the latest colour values into the cop list ready for the Amiga's display. Although I mentioned that this could theoretically support 224 extra colours, OutRun actually only uses up to 16 colours for the ground either side of the road and up to 64 colours for the sky. But this is a very simple and easy way of reproducing this fill effect for free. It means the main 68000 CPU can change the entire colour of a line simply by writing 2 values into the cop list. We need 2 writes because that's how AGA colours work on the Amiga. So using the Copper is a relatively simple idea that most Amiga programmers will be familiar with. But it's still an important concept to comprehend because, as we'll see in later episodes, juggling all of OutRun's colours into AGA's 256 colour limit was one of the toughest parts of this project. Thanks to the Copper processor and its ability to race the beam, we've just got our first swathe of colours effectively for free. Unfortunately, this is kind of where the hardware parallels between the two systems ends. So we've done the colours of the background. Now let's move on to rendering the road itself on the Amiga. There were a few major changes I made. For the first road, I wanted to remove as much computation as possible from the rendering code. MAME's graphics drivers spend a lot of time calculating pixels, checking whether they're in the screen bounds and other expensive operations. We don't have CPU time for that. I wanted a situation where I could simply copy the 320 horizontal pixels needed per line and be done with it. No boundary checking, no baggage, just copying data as quickly as possible. To do this, the Amiga version does something interesting when it initializes. It pads either side of the road with blank data, so the road graphic that is used as the basis to build up the final image effectively balloons from 512 pixels wide to 4096. Why would I waste memory in this way? Because it means that the code can be really simple. Simple is good because it equals fewer CPU computations. The end result of this means that for each road line, I can use a super fast move multiple instruction to copy data from the padded road ROM at a particular offset to the screen. I don't have to worry about checks and special cases, and not only that, but this doubles as a way of screen clearing the data from the previous frame, so you're effectively clearing that section of the screen for free also. So where are we now? We have the correct ground colours, correct sky colours, and now one of the two road generators is also working exceptionally quickly. However, I've skirted over a detail here which I need to explain. How does the road itself get coloured? Remember that we discussed how the original hardware colours the source graphic on a per pixel basis. Well, we definitely don't want to be passing the colour for every single road pixel we're rendering. That's tens of thousands of additional calculations per frame. The game would crawl. That approach might work for MAME, but it's not going to work on a Motorola CPU from the 80s. We know that really the road only has two colour schemes. Let's just call them striped and unstriped. How about we take the road graphic and pre-apply the colour scheme, then we swap completely between these two pre-created graphics based on which section of the road we're displaying, striped or unstriped. This immediately eliminates a huge amount of additional computation. Everything in development is a compromise, and the compromise with this approach is that it uses more memory. But it's definitely a worthwhile trade-off. This was a major breakthrough. Well done if you've got this far in terms of watching the video, but for better or worse, we're not done yet. If you remember, we've really only spoken about rendering the first road. OutRun has two roads that could be combined together. Now, at this point, you might be just saying, well, hang on, that's easy. You've done the first road, just run the code again for the second road. But unfortunately, it's not that simple if you want to do it in a fast and optimized way. If you remember, the way we rendered the first road was to basically eliminate everything that was already on that line of the screen. It blitted 320 pixels. With the second road, we need to keep the first road that's already there and somehow blend the second road in. So that's the challenge that we face. Now, the original hardware goes through a complex system of priorities where it blends pixels and looks at things on a pixel by pixel basis. That would again be very slow to do. So we needed to find a brand new approach to do this, not reuse, for example, what MAME does. And I don't want it to sound like I'm dunking on MAME or being negative about MAME. MAME is absolutely awesome. And what MAME does is try to document the arcade hardware as accurately as possible, and rightly so. However, this is a very different type of project, and we just can't take the same architecture and the same route that the MAME drivers took when it comes to emulating the graphics hardware. We've got to do things very differently. Now, I do most of my data noodling in spreadsheets to plan an approach, and I was wondering whether it would be possible to blit the second road using a logical OR instruction or operation. From a programming perspective, almost all CPUs have such an instruction, and if I could use this, I could blend the second road incredibly fast. To succeed with this approach, though, the pixel values themselves from the road layer would need to be compatible with the OR logic equation. This means feeding the two roads into the OR instruction would need to output the correct pixel value that matched the road mixing logic of the hardware. Now, as it turns out, I was able to remap the road pixels to make this work, and this was a major breakthrough. This is also one of the reasons that to run OutRun on the Amiga, a lot of the original ROMs go through a Python script first, because it is remapping various pixels on the road layer to make this possible. The final part of the road rendering was less of a breakthrough and more of a headache. With the previous approach, I could simply OR an entire 320 pixel screen width of data for the second road. The game would work, it would look correct. But this is a wasteful approach. The reason for this is twofold. Unlike with the first road layer, I don't need to clear the entire screen line. 320 pixels of data does not always need to be moved. It was possible that unnecessary data would be transferred, and this would slow the overall FPS of the game down. Secondly, the OR instruction, whilst light years faster than a manual pixel priority calculation, is slower than the move style instruction I was using for the first road layer. I therefore wanted to ensure that we were only using the OR instruction for necessary data. The challenge here is that the time saved by ORing less data could easily be consumed by a complex pre-calculation that attempted to figure out exactly what data should be moved. Sometimes the setup code needed for an optimization of this nature negates the overall saving. One way around ending up in calculation hell is to use pre-calculated values. In this case, I wrote a Python script to call out the leftmost and rightmost pixel of the road in the original graphics ROM along with its width. I then coded some somewhat crazy code to figure out whether that particular line of the secondary road was on screen based on the horizontal scroll, and finally I topped that off with an optimization to the original game code itself, which would hot swap the rendering algorithm based on which side of the road you were driving on. The latter part plays into the fact that we want to be able to use the move instruction more than the OR instruction to construct a road frame for speed purposes. Well done for making it to the end of this odyssey. There's going to be probably another 4 parts in this series if there's interest. If at least one person subscribes to the Patreon, I'll have to go ahead and start making the rest of them, so please do that. There is a link to the source code in the video description. It's not really intended to be a tutorial for Amiga programming, but if you watched this video and found it a little bit basic, or you thought, I need to look at the source code to really understand what on earth he's on about, then please do so and go ahead. But thank you very much. Thanks to everyone that supported the project, and I'll see you in the next one.